Chapter 2: Internal Energy, Work, Heat, and Enthalpy. Section 2.9: Adiabatic Processes. A system may be surrounded by an adiabatic wall or a diathermal wall. A diabatic wall does not allow energy transfer. Q is 0. A diathermal wall allows energy transfer, so Q is very likely non-zero. DIA is a prefix that means across. For example, in the words diameter, diagonal, and over here diathermal. In an adiabatic process, Q is 0. There's no heat transfer. And there are two subtypes of adiabatic processes: reversible or irreversible. In a reversible process, P is equal to P external. In an irreversible process, there is a finite difference between the system pressure P and the external pressure. Now, how do pressure, volume, and temperature of an ideal gas change in a reversible adiabatic expansion or adiabatic compression? We have this derivation. First, Q is 0 for the adiabatic process. Therefore, dQ is also 0. du is equal to dW. dW is negative P external dV. For a reversible process, P is equal to P external. Therefore, du is equal to negative PdV. The internal energy of an ideal gas depends only on its temperature. Again, this is just because the potential energy of an ideal gas is always 0, and the kinetic energy can be determined by its temperature. Therefore, we have this equation: du sub T is equal to 0. If temperature is held constant, then du is 0. And therefore, du can be separated into two components. It's du sub V and du sub T. It means the internal energy depends on volume and temperature. You may ask, does this internal energy depend on pressure? The answer might be surprising. Yes, the internal energy does depend on pressure, but we do not write a third component here. This is because pressure depends on V and T. Out of PVT, there are only two independent variables. So you can write U as a function of VT or PT or PV, but you do not write this U as a function of three variables at the same time. That's going to be misleading. So again, we can assume this U depends on volume and temperature. And because dUT is just 0, so du is just dUV. dUV, that means the internal energy change in an isochoric condition. And therefore, dUV is dQV, and dQV is CVDT. So for a adiabatic reversible process, we have du is equal to CVDT. It sounds strange, because in this process, volume is not held constant. But still, we can write du is equal to CVDT because the system is an ideal gas. Again, for an ideal gas, well, the internal energy only depends on temperature. Therefore, we can write this. And therefore, CVDT is equal to du, and du is equal to negative PdV. We can put these two together. And the pressure is nRT over V for an ideal gas. So we have this equation. And do not integrate both sides yet, because if you look at the right hand side, it contains two variables. It contains V, it contains T. On the left hand side, well, it contains only one variable, but just because on the right hand side there are two variables, we have to solve this issue first. The simplest way is to divide both sides by temperature. And then we have CVDT over T is equal to negative nR over V dV. Now if you examine both sides, on the left hand side it contains only T. On the right hand side it contains only V. And we can integrate both sides, and we can have the lower limit and upper limit of the left integral to be from Ti to T final. And over here it's from Vi to V final. In a reversible adiabatic expansion or compression, we have this equation: CVDT over T is equal to nR dV over V. Now we integrate both sides. And the integral of dt over t is the logarithm of t. the integral of dV over V is the logarithm of V. Therefore, we have this equation after integration: CV times the difference between LNT final minus LNT initial is equal to negative AR times LNV final minus LNV initial. We need to know how to deal with logarithms. The difference between two logarithms is the logarithm of a division. So we have this here, and we have ln v final over v initial on the right hand side. Both sides divided by CV, and then we have this equation. And now, again, if we raise e to the power of this logarithm and e to the power of this logarithm, we get this equation. T final over T initial is equal to V final over V initial to the power of negative NR over CV. NR over CV can be written as R over CVM if we divide both the top and the bottom by the number of moles N. So again, the temperature ratio is equal to the volume ratio raised to the power of negative NR over V. Therefore, given the volume ratio between the final and the initial state, which is V final over initial, we can somehow calculate the temperature ratio. Now, very often we're given both the initial volume and the final volume, or sometimes the problem tells us this information: the volume of the system is doubled in a reversible adiabatic process, and then this ratio is just 2. Or some people can just simply tell you the volume is tripled, the volume is quadrupled, and then you know what the ratio is. When the volume decreases, we call that a compression, and when the volume decreases, the internal energy increases. This is just because we're talking about an adiabatic process, so Q is 0, and then the system is compressed, so work is positive. Therefore, Q plus work is greater than 0. Delta U is greater than 0. And if delta U is greater than 0, the internal energy increases. And because the potential energy is always 0 for an ideal gas, that means the kinetic energy increases in the compression process. If the kinetic energy increases, we know the temperature increases. On the other hand, if the volume increases, its expansion, the system does work to its surroundings, work is negative, and Q is 0 for this adiabatic process. So overall, the internal energy decreases, the kinetic energy decreases, the temperature decreases. That explains this negative sign over here. If V final is greater than V initial, and then this is less than 1, TF is less than TI. If VF is smaller than VI, well, it's compression, and by looking at this equation, this value is going to be greater than 1. Temperature is going to increase. In a reversible adiabatic expansion or compression, we have this equation. The temperature ratio is equal to the volume ratio to the power of negative NR over CV. And also, NR over CV is simply R over CVM. For ideal gas, Cp minus Cv equals NR. We'll prove this. When PVT of an ideal gas change, we may assume the internal energy and enthalpy of the system depend on only 2 of the 3 variables. Again, PVT, there are 3 variables, but only 2 are independent variables. The third one is treated as a dependent variable. So we can write this formula: du is equal to du sub v plus du sub t. So when we write this, we assume internal energy is a function of 2 variables, volume and temperature. So over here, we hold volume constant. We allow temperature to change, and we get the internal energy change based on temperature change. Here, temperature is constant. This is how internal energy change when the volume changes. So we have these 2 together, but remember, when temperature is constant, the internal energy of an ideal gas remains constant. So this part is simply 0. Therefore, du is simply du sub v for an ideal gas. And du sub v is dq sub v. And dq sub v is Cv dt. Now we'll do similar analysis to dH. We're going to assume H is a function of 2 variables, pressure and temperature. Again, H also depends on volume, but that dependence is included in these 2 terms implicitly already. And now we can expand this. This H is just U plus PV. So we have 3 terms now. It's dH with constant pressure, and du over sub T, and dPV sub T. remember this du sub T is just 0 for the ideal gas, because if you have an ideal gas, the potential energy is always 0, and if the temperature is constant, the kinetic energy remains unchanged. So this du sub T is 0. The PV sub T is also 0 for ideal gas. It's just because PV equals RT, and if temperature is constant, PV is constant. So actually, the last two of the three components are both 0. dH is just dH sub P for an ideal gas. Therefore, for an ideal gas, we have this equation: dH is dH sub P is equal to dQ sub P is equal to Cp dt. Now we can take the difference between these two equations. Cp dt minus Cv dt is simply dH minus du. dH minus du, based on the definition of H, is simply dPV. dPV is dnRT because it's an ideal gas, and dnRT is nR times dt because n and r are constant. And both sides divided by dt, we have Cp minus Cv is equal to nR. And now we can rewrite this equation for the adiabatic reversible process. The temperature ratio is the volume ratio to the power of negative nR over Cv. And nR is actually Cp minus Cv. So we can rewrite this to be Vf over Vi to the power of 1 minus gamma. What is gamma? Gamma is just defined to be Cp over Cv. So this is just for convenience. For some gases, some solids, liquids, if you are given the value of gamma, you know what Cp over Cv is. Gamma is always greater than 1. Except one rare exception, which is water at 4 degrees Celsius, and then gamma is 1. Gamma is never less than 1. Gamma is always greater than 1. Because Cp is n times Cpm, Cv is n times Cvm, so gamma is also Cpm over Cvm. Now let me give you one example. If you have a helium gas, Cvm is 1.5 R. Cpm is then 2.5 R. So the value of gamma is 2.5 over 1.5, which is 5 over 3. In a reversible adiabatic expansion or compression process of an ideal gas, the temperature ratio is the volume ratio to the power of 1 minus gamma. And again, gamma is Cp over Cv. Gamma is Cpm over Cvm. What if you have a molecule, for example, a diatomic molecule, and usually Cvm is 2.5 R. Cpm is thus 2.5 plus 1, 3.5 R. And gamma is then 7 over 5, which is 1.4 for many diatomic molecules in the gas phase. And this equation is often used to calculate the final temperature given the initial temperature, as long as we know the ratio between V final over V initial. So if I'm telling you it's a helium gas, then gamma is 5 over 3, and I tell you the volume is doubled in this adiabatic reversible expansion or compression, well, then you just plug in all the numbers. If the volume ratio is 2, just plug in 2 here. If gamma is 5 over 3, just plug in 1 minus 5 over 3 on top. And then you'll be able to get the ratio between T final and T initial. If you know what the value of T initial is, you can easily compute T final. Again, this equation applies to an ideal gas that undergoes reversible adiabatic expansion or compression. Now, if we know T final, T initial, it's very simple to get the change of the internal energy, because du is Cv dt for an ideal gas. dH is Cp dt for an ideal gas. So delta U is just Cv times delta T. Delta H is just Cp times delta T. Again, the difference between delta U and delta H is delta PV. By definition, delta PV is simply delta nRT. Delta nRT is simply nR delta T. And also Cp and Cv differ by nR for an ideal gas. And again, Q is 0, so if you have the value of delta U, it's also the value of work, because work is delta U minus Q, and Q is 0 for this adiabatic process. Again, in a reversible adiabatic expansion or compression, we have the temperature ratio is equal to the volume ratio to the power of 1 minus gamma. Gamma is Cpm over Cvm. It's always greater than 1 except one case, which is water at 4 degrees Celsius. As the volume increases, the system loses energy. Since the P is always 0, then we lose kinetic energy. The kinetic energy of the system decreases in this adiabatic expansion. On the other hand, if it's compression, then the kinetic energy and temperature of the system both increase. We can also compute the pressure ratio. How do we do this? Well, we go from here, the ratio between V final and V initial to the power of 1 gamma over here is equal to T final over T initial, right? And the temperature is simply PV over NR. So T final is P final, V final over NR. T initial is P initial, V initial over NR. And we can cancel NR and NR, and we have P final, V final on top, P initial, V initial on the bottom. And somehow we can just move this V final over V initial to the left hand side. For example, we can divide both sides by V final and multiply both sides by V initial. Alright, and then we have P final over P initial is equal to V final over V initial to the power of negative gamma. Again, gamma is usually just greater than 1. So that means the rate of the decrease of pressure is faster than the increase of volume, right? By just looking at this equation, because this gamma is greater than 1. Also, we can relate the temperature ratio to the pressure ratio. That's just algebra, because from this equation, we can just have left and right to the power of negative 1 over gamma. So this part to the power of negative 1 over gamma, we get just V final over V initial. We put it here. And this part to the power of negative 1 over gamma, we put it over here. Alright, so we get this equation. And again, T final over T initial is V final over V initial to the 1 power of gamma. And we can express the volume ratio in terms of pressure ratio. And we put everything together. We relate the temperature ratio with the pressure ratio. It looks a little complicated. Alright, it looks a little complicated. It's PF over PI to the power of 1 minus 1 over gamma. So again, pay attention to this negative sign here. That's why you have negative 1 over gamma and you have positive 1 over here. Pay attention to the signs. Now some numerical examples. Let's look at 2.9.1. Ideal monatomic gas expands until its volume doubles in a reversible adiabatic process. The initial temperature is 300 Kelvin. Calculate its final temperature first, and then calculate delta U, delta H, Q, and W. So, if we have a ideal monatomic gas, there's no rotational motions, no vibrational motions. So we just need to look at the translation. In each dimension, the molar heat capacity is 0.5 R. 3 dimensions, 1.5 R. So CPM is equal to 1.5 R plus R. We get 2.5 R. What's the value of gamma? It's just 2.5 over 1.5. That's 5 over 3. Now we have the temperature ratio is equal to the volume ratio to the power of 1 minus gamma. We plug in the value of gamma. Well, it's 5 over 3. 1 minus 5 over 3 is negative 2/3. And we got this number 0.63. So T final over T initial is 0.63. Plug in the value of the initial temperature. T final is 189 K. This temperature is lower than the initial temperature only because the system did expansion. It loses energy that way. Now for an ideal gas, the internal energy and enthalpy only depend on temperature. Delta U is integral of Cv dt. We get this number. Delta H is Cp dt. We get this number. Alright, or you can say delta H is delta U plus delta PV. So given delta U over here, negative 277, and then delta PV is simply just delta nRT. Delta nRT is nR delta T. And you can compute delta T easily. We get this number. What about Q? Q is just 0 because it's adiabatic. W is just delta U because Q is 0. Now let's look at the irreversible adiabatic process. Okay, it's a little bit more tricky. Let's look at an adiabatic process. That means Q is 0, and let's assume the process is irreversible. P is different from P external. For convenience, we'll just say, how about we're just use a constant external pressure. All right, a constant external pressure. Again, we'll just derive first. Q is 0 because it's adiabatic. Delta U is Q plus W, and because Q is 0, so delta U is just equal to W. W is negative P external dV. And over here, we need to have this equation. Why is that? Because usually the system expands until its pressure is equal to the external pressure. So we can assume P final is P external. Okay, this is when the expansion or compression stops. So negative P external delta V is negative P final delta V. And P final, we'll just copy that. Delta V is V final minus V initial. And then over here you can see, well, clearly it's just P final times V initial minus P final times V final. Alright, I'm going to use P final, V final as the common factor. I put it here, and it's going to be the P final times V final times this VI over VF minus 1. Alright, where does this come from? So if you multiply this P final, V final, and VI over V final, well, you get P final times V initial. P final times V initial, right? Over here. There are two negative signs that cancel. Also, we have negative P final, V final, so it's right here. Negative 1 times P final, V final. The reason I put it this way is just because P final, V final can be written as nRT final. And over here, very often we will be given the ratio between the initial and final volumes. Alright, we can calculate delta U in this way because it's an ideal gas. For ideal gas, delta U is always integral of CV dt, so it's just CV delta T times CV, it's just CV times T final minus T initial. Now we have delta U, we have W. Alright, W is here, delta U is here. And we know delta U is W because Q is 0. So over here, this is delta U is equal to W plus Q, and Q is 0. Alright, so we have this equation. So if you look at this equation, if we are given the value of CV or molar CV, we have this. And if we're given the initial temperature and the ratio between the initial and final volumes, we'll be able to solve for TF. Because in this equation, if we're given this ratio, this becomes a number. NR usually are provided, and then if CV is also provided, this equation contains only one variable, which is T final. We just solve for T final. Alright, once we have T final, we'll just get delta U, right? Or get W. We can also get delta H, right? Delta H is the integral of Cp dt for ideal gas. So we'll get this formula. So it's easy enough to get delta U, delta H, and W. What about Q? Q is just 0 because it's adiabatic. Oh, just remember, we're talking about the irreversible process. So the difference between the system pressure and external pressure is finite. And also, for convenience, we'll just say this external pressure is a constant. It's easier to calculate that way. Now another numerical example for an adiabatic process, but this time it's irreversible with a constant external pressure. So we're going to just use this equation right away from the previous page over here. We derived this. So I'm not going to derive this again. I just want to show you the rough idea. The rough idea is this: Q is 0, so delta U is W. Delta U is the integral of CV dt, and W is simply negative P final times delta V. Why is that? It's just because at the end of the expansion of compression, the P final should be equal to P external. Otherwise, the expansion or compression should continue. Alright, get back to this. I'm going to just use this equation. Now let's read the question again to get the information. The volume is doubled, so therefore VI over V initial is 1 over 2, because after this process the volume is doubled. V final is 2 times V initial, so we have this information. We do not know final temperature. We do have the initial temperature. I think it's 300 Kelvin over here. And we have the molar isochloric heat capacity for this ideal diatomic gas, roughly 2.5 R. So we're plugging 2.5 NR here because this is CV. CV is N times CVM. And if you look at these two sides of the equation, we see n here, they cancel. I see r and r, they cancel. We get this equation. And then we plug in T initial is 300 Kelvin. We solve the equation, we get 250 Kelvin. Now for ideal gas, its internal energy change is simply the integral of CVDT. And then we plug in the numbers, so we get this number. Q is 0, W is delta U minus Q, so W is equal to delta U. Delta H is just delta U plus delta PV. Delta PV is just NR delta T. So we get this number. Or you can simply calculate this delta H in this matter. It's the integral of Cp dt, and it's just n CPM dt. So we have n here. We have CPM here. CPM is CVM plus R. We have delta T here, T final minus T initial. And we get the same value for delta H. So there are two different ways to compute the enthalpy change. They both result in the same value, negative 291 joule, for this numerical problem. Again, this is not isochoric, this is not isobaric. However, we can still, do this calculation. We can still say du is CVDT, dH is CPDT, because our system is an ideal gas. When you have an ideal gas, the internal energy and enthalpy only depend on temperature, and therefore for the calculation of the change in internal energy, we can always divide the process into two steps. The first step, make sure it's isochoric, and then we can use integral of CVDT. The second step, make sure it's isothermal, and then the internal energy change is just 0. How do we compute the change in enthalpy? Again, two steps. The first step has to be isobaric, and then you can calculate delta H. Delta H is simply Q sub pressure, Q sub P. That's just the integral of Cp dt. Alright, we just calculate that step, isobaric. The second step, make sure it's isothermal. If it's isothermal, delta H is just 0. So overall, delta H is still the integral of Cp dt. So this is a trick to compute delta H and delta U for an ideal gas. Do not do that for solids and liquids.